Welcome back to The Explainer. When we look up at the night sky, it's easy to think of stars as these eternal, unchanging fixtures, right? But here's an absolutely wild concept that totally reshapes how we learn about the cosmos. Every single star out there has a lifespan, literally. Just like us, they're born, they age, and yeah, eventually they die. Some just kind of quietly fade into the background, while others, well, they go out in these spectacularly violent explosions that can literally outshine whole galaxies for a brief moment.
So that brings us to the big fundamental question. Why do stars die at all? I mean, how do these massive, glowing spheres of gas that have been burning for billions of years suddenly meet their end? And, maybe more importantly for us, is our own sun going to face that exact same fate one day? Let's dive into one of the most spectacular and honestly mysterious events in the entire universe.
Here is our roadmap for today's explainer. First, the birth of stars. Second, the crucial balance. Third, path A, small star death. Fourth, path B, massive star death. Fifth, the extreme leftovers. And finally, number 6, we are star stuff. Let's get right into it.
Section 1. The birth of stars. So stars don't just magically pop into existence out in the void. They're actually born inside these massive cosmic nurseries called nebulas. Picture enormous swirling clouds of gas and dust. Over immense stretches of time, gravity goes to work. It slowly, relentlessly pulls all this floating material together. And as more and more gas collects in one specific spot, the center of that condensing cloud starts getting incredibly hot and super dense.
Now, for a star to actually be born, that core has to hit a staggering 15 million degrees Celsius. Yeah, 15 million. As gravity crushes all that gas inward, the temperature just skyrockets, and once it crosses that extreme threshold, a massive cosmic trigger gets pulled, kicking off the star's actual life.
And that trigger is nuclear fusion. At 15 million degrees, the hydrogen atoms inside the core are moving so incredibly fast, and they're packed in so incredibly tight that they literally smash together and fuse into helium. This fusion process is basically the engine of the star. It releases a massive amount of energy, pumping out the brilliant light and intense heat we eventually see from light years away. As long as this fusion engine keeps running, the star stays alive and well.
Which brings us to Section 2.
The crucial balance.
Every single second inside a living star, there is this epic cosmic tug-of-war going on. On one side, you have gravity. Gravity never sleeps. It's constantly trying to crush the immense, staggering weight of the star inward on itself. But pushing back, you have the energy from that nuclear fusion we just talked about, violently forcing material outward. A star only survives because these two massive opposing forces are perfectly balanced. It's a delicate equilibrium, but it can hold steady for millions or even billions of years.
But here's the catch, and it's a crucial one. Fuel is limited. The star's supply of hydrogen isn't infinite, so eventually it starts to run out. And when it does, that fusion engine starts to sputter. It slows down, the outward pressure drops, and suddenly gravity takes the upper hand. This is the beginning of the end for the star. Now, exactly how this final chapter plays out depends entirely on one single variable: mass.
Let's look at Section 3. Path A, small star death.
So what happens to smaller stars, kind of like our own sun? Well, as the hydrogen runs out, gravity shrinks the core. But paradoxically, the star's outer layers actually do the exact opposite. They expand enormously. The star balloons into what we call a red giant. To give you a sense of just how terrifyingly huge this is, if our sun became a red giant right now, its outer layers would swell up so much they'd engulf Mercury, Venus, and, yeah, very likely our own Earth. It's just massive. Eventually, the dying star just can't hold on to those huge, puffed-up outer layers anymore. They gently drift away into deep space, creating this absolutely stunning cloud called a planetary nebula. Now, a quick heads up, the name is actually a bit of a historical mix-up. These glowing clouds literally have nothing to do with planets. Anyway, as those outer layers float away, the only thing left behind is the star's exposed, scorching hot core, a tiny, super-dense object we call a white dwarf.
Moving on to Section 4, Path B, massive star death.
Now, for really massive stars, things get a lot more dramatic. Their fusion engine doesn't just stop at helium. Because they have so much mass, and therefore so much gravity and heat, hydrogen fuses to helium, helium fuses into carbon, and carbon fuses into oxygen. It just keeps going down the periodic table. But step 4 is the fatal one. Eventually, the core starts producing iron.
And iron is an absolute death knell for a star. Why? Because fusing iron doesn't release energy, it actually absorbs it. The second the core becomes mostly iron, fusion violently, instantly stops. The outward pressure vanishes completely, and gravity crushes that giant core inward in less than a single second.
This collapse is so insanely fast and violent that the incoming material literally bounces off the super-dense core, triggering a supernova. Gravity finally wins the war, and the result is one of the most powerful explosions in the known universe. It is mind-blowing. For a brief moment, this single exploding star can shine brighter than an entire galaxy containing hundreds of billions of stars. It is the ultimate cataclysmic finale.
Let's check out Section 5, the extreme leftovers.
So, the smoke clears. Depending on the star's original mass, it leaves behind one of 3 totally bizarre cosmic corpses. Like we saw, smaller stars leave behind white dwarfs. These are roughly the size of Earth but pack the mass of our entire sun, and they just slowly cool down over billions of years. But massive stars? Their crushed cores become neutron stars, squeezing a sun's worth of mass into a sphere just 20 kilometers across. Some of these, known as pulsars, actually spin hundreds of times a second. And then, at the absolute extreme end, the most enormous stars create a gravitational pull so intense that not even a neutron star can hold up against it. It crushes inward infinitely until a black hole forms. Gravity becomes so strong that literally nothing, not even light, can escape it. The star just vanishes from the visible universe forever.
To really wrap our heads around how incomprehensibly dense these leftovers are, just think about this number: 1 billion tons. If you were to take a standard kitchen teaspoon, fly out to a neutron star, scoop up just 1 teaspoon of its material, and bring it back here to Earth, that single teaspoon would weigh 1 billion tons. That is the sheer extreme level of physics we are dealing with when gravity finally wins. And that brings us to our final section, number 6. We are star stuff.
Because here is the truly amazing takeaway from all of this. Without dying stars, you and I wouldn't even exist. Think about elements like carbon, oxygen, calcium, and iron. These are the literal building blocks of life, right? Well, they weren't just sitting around since the Big Bang. They were actually forged inside the crushing, burning cores of ancient, massive stars. And when those stars died and exploded as supernovas, they blasted those exact elements out into the vast emptiness of space. Over billions of years, that scattered ash clumped back together to form new stars, rocky planets, and eventually us.
Which leads us perfectly to this famous quote from the legendary astronomer Carl Sagan: "We are made of star stuff." It sounds like just a beautiful, poetic metaphor, but it's a literal scientific fact. In a very real, tangible sense, every atom of carbon in your cells, every bit of oxygen you're breathing right now, and the iron pumping through your blood, all of it was once inside a living, burning star that lived a wild life and died a spectacular death just so you could be here. So, as we wrap up our learning journey today, I want to leave you with a thought. If the dramatic, destructive death of a massive star is actually the birthplace of the very atoms inside your body, what new beginnings in your own life might come from an ending? Next time you look up at the night sky, remember that some of those peaceful little lights are gearing up for one final breathtaking exit, an exit that will literally see the future of the universe. Thanks for joining me on The Explainer today. Keep learning, keep looking up, and never ever stop asking questions.